Welcome to today's Technology in Space session. I'm delighted to welcome all of you to what I can only expect is going to be a fantastic panel discussion with some brilliant people doing amazing work in Mars research, using all sorts of technology to help them get that amazing research done. I'm also joined today by my fabulous Mars plushie as the guest of the week, and I hope that everyone is enjoying Mars Day. And I know that it's bumper packed. There's so many amazing events taking place today. So thank you everyone for joining today's session. So we're going to kick off with a little bit about myself before I introduce you to our amazing panelists. So I'm Patricia Skelton. I'm the Deputy Head of Astronomy Engagement at the Royal Observatory in Greenwich. So I work alongside our astronomers at the Royal Observatory to deliver our astronomy engagement activities. So that includes things like hosting schools' workshops and planetarium shows, as well as public engagement activities, including public planetarium shows, as well as doing some amazing stuff inside our planetarium. Some of you who are watching today's session may have actually visited us at the Royal Observatory Greenwich. Maybe your teachers have brought you along for a visit. One of the things I love about my job is that I have the opportunity to talk to people about space exploration and astronomy, and I get to do that every single day. We're also really lucky because we have a planetarium, and I like to call our planetarium the tour bus of the universe because it can take us anywhere we want to go. So if we just want to hop to the moon, we can do that. Hop over to Mars, of course. Do you want to travel to the edge of a black hole? We can do that as well. So we have so much fun inside our planetarium, and it's a wonderful way to get everyone excited about astronomy and space exploration. I wasn't always a science communicator because that's sort of what I do now. I actually worked at university before joining the Royal Observatory Greenwich. I was a lecturer and I taught students some undergraduate astronomy. And one of the modules that I also taught was the practical module. So I trained students up on how to use telescopes to do astronomical research. So that was collecting data and all sorts of interesting objects. And then once you've got that data, what you have to do with it to get all that information out of those objects that you're studying. I have always loved astronomy and space exploration. And I think the thing that made me really excited about both subjects was my love of science fiction. So that's one of the things that I really do love. I'm a huge Star Trek fan. Maybe some of you watching the same, maybe some of you came into astronomy or space exploration through different ways. It doesn't matter how you got in. We welcome everyone who has that shared love of astronomy and space exploration. In terms of my love of the planet Mars, well, that began all the way back in 1997 when a little rover called Sojourner trundled onto the surface of Mars. I remember the excitement of seeing this teeny tiny little rover exploring the surface of Mars, and it was amazing. It was not something that I thought I was ever going to see in my lifetime. And now look at where we are now. All the amazing spacecraft we've already sent there, plus the new spacecraft that we're planning on sending in the future. So I'm certainly very excited about Mars Day. And what I love about today's panel is that we're going to be looking at the technology that allows us to do our exploration out into the solar system and also exploration of the universe as a whole. So I'm going to introduce you now to our amazing panelists, and they're going to talk to you a little bit about what they currently do, and then we'll have a discussion about what got them onto the path that they're on now. So I think we're going to start today with Daisy. And Daisy, it's lovely to meet you again. I know we had a little bit of a catch up last week as we were planning for today's session, but can you tell us about the amazing work that you do every day?
Sure, no problem. So I work currently at Goonhilly Earth Station. So I know a lot of you guys have been there today, and you guys have been listening to some of the amazing colleagues I have down there. And I am a software engineer for Goonhilly, which essentially means that I get to talk to a wide variety of people that work there, and create software that helps them with their jobs. It's quite a satisfying job, and very rewarding. But I've not always done that. I've not always worked in that sort of region. So It all kind of started back in 2018. I had an interest in physics and I was doing my A levels at the time, and I joined the CANSAT competition and competed that year in York. And you can see on the left there, tiny me and our CANSAT. And we won, we became UK champions that year. And so that allowed us to go and compete in the Azores. And this competition, it was all about designing a satellite that would fit inside the dimensions of a tin can. And it still goes on today. And I'm now a judge, so schools feel free to ask any questions about that and have a Google. So yeah, we got to compete with all of these amazing the teams in the Azores there. And after that, because I think partially because I was a girl, but also because I had such an interest and I really enjoyed the competition, it opened up loads of opportunities to me, which really showed me that, you know, I wanted to stay in the space industry. So after that, I got invited to go to the 2019 Space Conference, where I met loads of really cool people. I met Tim Peake. I got to speak to loads of space companies there and kind of really get a feel for what the space industry was like. And it taught me that CANSAT was basically a perfect representation of what it would be like working on a real life space project. And so I knew instantly that that was the industry I wanted to go into. So meanwhile, I was studying at university, and the Catapult, which is a big company here in the UK, put on what's called spinternships. They are basically internships in the space industry. And I applied for one of those after seeing them available at the space conference that I was at. So I did mine in engineering origami, and I designed a habitable space module that would take concepts from origami. So the orange folded structure there is probably more of what I focused on my design on. It kind of looks a little bit like that. And there was a lot of maths and a lot of computing, which before I did my internship, I absolutely hated. But I grew to love that during my internship and developed a really good skill through doing that. And I did that with a company called B2 Space. And I was enjoying it so much that I kind of asked if I could stay. I know one of the panelists earlier kind of had a similar story and seems to work well in the space industry. So yeah, I asked if I could stay and work there, and I got to join the analysis team there after I graduated from my degree. So here's just a picture of me showing off that I graduated. So my degree was in physics with astrophysics, just for anyone wondering. I know it can be a bit tricky to choose your degree to know where to go with it afterwards. So this was me when I first started working at B2 Space. I got to do a lot of analysis work. I designed and built my very own rocket, which you can see in the top picture there. It doesn't look like much. It was made out of a drain pipe, but it worked. And the idea behind B2 Space is that they launch high altitude balloons and then launch rockets from them. And it's a very new concept. It essentially means you can save a lot of fuel and money and allows small companies to take their projects to space. But then I still carried on doing some really awesome projects. So here's me at another conference. And then on the right, I actually got invited to go to Downing Street last year and talk about education and how that involves space, which is really fun. And now it takes me to the present day. So here's some pictures of Goonhilly. So I'm currently working there. I work remotely, but I have been down to the site, and it is very, very impressive, as I'm sure lots of people have been saying this morning from their visits. And of course, I had to include a picture of one of the alpacas there in the top. So yeah, I'm happy to answer any questions about getting into the industry, but I know that there are other panelists, and I'm really keen to hear their stories too.
Oh, that's wonderful. Thank you so much, Daisy. And actually, you do have a question that I'd love to run by you. And it's about the CANSAT. So can you tell us a little bit more about what a CANSAT is?
Sure. So it's a small competition. It's run by the European Space Agency, and so the UK side of that is run by UK Space Agency and STEM UK. And it's held every year. You choose a secondary mission. So you're given a primary mission of measuring, I think it's temperature and pressure. And you have to be able to transmit that back down to a ground station, which is essentially just a smaller version of Goonhilly. It's just a teeny tiny version of that. And then you have to process that information and data and present your findings. So you can choose to measure anything else as well as that. You can choose to measure what we chose was ozone, and you have to have a scientific objective behind that. So that might be seeing if a planet is suitable to sustain life, or it could just be as simple as being able to land it on some legs, which I say is simple, it's really not simple. But it doesn't have to necessarily be measuring something, as long as you've got some form of scientific objective. It has got certain requirements, like a real space mission does. So it has requirements. It has to descend at a certain speed. So you end up designing a parachute, and it has to have a certain weight as well. Again, just as a real space mission would. And it's for a variety of ages. I believe you can enter pre-GCSE and then you can enter all the way up. I think we have had a university team as well. And there's a couple of launches. So there's one that's a sort of practice launch before the real competition, and then there's one this year, it's in April, which is the final, where you launch it. And you I think this year it is launched from real rockets. When I did it, it was from a weather balloon, but this year it's real rockets that launch the CanSat. And essentially, while it's coming down, that's when you collect your data, and then you present it to us judges, and create a nice little PowerPoint slideshow for us to have a look at. And you also do reports as well throughout, so it's not just all relying on that. There is other work too.
Oh, that sounds amazing. And hopefully some of the students watching today might be inspired to participate in that. Oh, that's wonderful, Daisy. Thank you so much. And I think what we'll do is we'll move on next to Eddie. So, Eddie, if you'd like to introduce yourself and tell us about the amazing work that you do.
Yep, sure thing. Thanks very much, Patricia. So, yeah, my name's Eddie Ross, and in a second, hopefully, there'll be some slides that hopefully you can all see. So, I am currently a senior systems engineer, and I work for this company whose name's at the bottom left-hand corner, which is called Thales. So, they're a global group engineering organization that delve into all sorts of areas of engineering, including the space sector. And they're based from France as their headquarters. And so what I thought I'd do before kind of talking a little bit more about what I do now is like Daisy, just give you a bit of an understanding about how I got to where I got to today, and a bit of a what did I do in terms of the role and the subject, but also kind of what I wanted to do, and how that changed along the sort of my evolution as an engineer and as a person, from a student to an employee. So in my GCSEs, I did maths, English, science, art, French, music. So kind of dominated a little bit more by the kind of humanities sort of subjects. And at that point, I wanted to be an artist or a designer or a musician. Didn't care at all really about space and science at that point. But started to get a little bit more interested when I moved to be an A-level student. I got into sort of sci-fi, just as Patricia said. I thought that sounds quite interesting. But I never really wanted to do the science myself. So I once upon a time thought, well, maybe I'll just be a journalist and talk about the interesting stuff that's happening around the world to do with science, or maybe go into being an architect, or become some kind of a scientist. I went to university and I did 2 degrees. I did a physics and astrophysics, and then I did an astronautics and space engineering degree. At that point, I started to realize, well, maybe I want to be an astronaut, or maybe I want to be a space engineer. And I did a project there that was relating to Mars, which was, this was a little while ago now, it was about 10 years ago. But it was what happens if we were to just try to leave to go to Mars now? What technology is out there that would allow humans to stay alive as they were venturing over to Mars? So I did an environment control and life support system project there for a a near-term mission to Mars. Following that, I then got my first job as an engineer. That was a company called Teledyne TV, which is based down in Essex. At that point, I started to get into the design of satellites and quantum technologies. So as a real kind of space systems engineer, and that company that I worked for essentially makes all of the imaging sensors that you potentially have always ever seen images of space from, particularly rovers that are on Mars. So worked on some of the sensors that made its way onto the ExoMars missions. Then I decided that I wanted to do a PhD. I wanted to get into some more data science. I felt like I hadn't got any of that. So I did an astrophysics PhD where I was looking at solar physics and space weather. At that point, I realized I did like being a scientist, but I still really liked being a space engineer. So I decided I wanted to go back into the space industry, and that's when I worked for the company that Daisy's mentioned before, the Satellite Applications Catapult. I was the knowledge exchange manager trying to get the UK space sector to do research between academics, people at universities, and then the industry players, so people in companies that are actually making products. And then following that, I then ended up where I'm at today. So I'm based in Manchester, working for this company, Thales. Not working in space, unfortunately. I'm working in maritime autonomy. So that's making boats that can self-drive, but still really ultimately want to be a space engineer. So if I just skip ahead, one of this I think this slide basically really summarizes everything that I'm keenly interested in the space sector. So I'm interested in building satellites. I'm interested in the sun and how the sun interacts with the Earth, and also interested in keeping the Earth protected. And one of the things that I've been involved in is building satellites and sort of specific payloads that go into satellites. And this is one of these quantum technology satellites that I've been involved in. And this one's a very interesting one because it's about the size of a shoebox. It's called a CubeSat. It's about 30 centimeters by 20 centimeters by 10 centimeters. And I was involved in designing and making this. So really, really exciting kind of, satellites, you tend to think of them as huge things, but actually the size of a shoebox. And then eventually, I'm where I'm at today is working on things like this. So building boats that can drive on their own without having any humans on them, because these boats are tending to be used in sort of dangerous operations like clearing mines out of the ocean. So they're being used for the greater good, but it's quite a dangerous game for humans to be in. So hopefully that shows you that my career path today has not been a very straight line. It's been all sorts of wibbly wobbly, and I've gone to kind of wherever the wind's taken me and my interests have taken me. And I thought I'd just kind of focus, seeing as we're in a sort of technology in space, I thought I'd stop talking so much about me and just talk about some interesting things, maybe just kind of share some wisdom. So there are kind of four main types of satellites. There's Earth observation, so those ones are kind of looking down, taking pictures of the Earth. Communications, so you may have heard of Starlink. It's kind of the obvious one that people talk about now from SpaceX. So that's providing the ability to talk to each other around the Earth. Navigation, so that's basically a global positioning system, which is an American one, or in general they're called Global Navigation Satellite Systems (GNSS). And then also there's just general science, so telescopes that are taking pictures, for instance, of Mars, or rovers going to Mars, or space stations, which I think we've heard about today already. And they come in all sorts of different shapes and sizes. So I've already showed one which is a CubeSat, and there's a CubeSat which is in this top right-hand corner over here. So that's a 10 by 10 by 10 centimeter. So you can see it's kind of the size of a fist. But then you get some which are kind of bus-sized, and then even larger than that. And they kind of range anywhere from being as small as ducks or as large as rhinoceroses. So yeah, quite interesting diversity in satellite shapes and sizes. And in terms of some of the things that they do, there's very interesting technology on satellites in that if you took a picture on a cloudy day, so this one, I'm based in Manchester, so this is a typical Manchester sky, very cloudy. If you were trying to look at what's happening on the ground in Manchester, this is what you'd see, and you can't really see anything. But satellites can take all sorts of types of images. So you could take images using radio waves, and that's a synthetic aperture radar. So using radar technology to take a picture, and that's getting through the cloud. So it may look like that if you're using your regular camera, but using radar, then you can start to really picture the ground. So this is one interesting piece of technology that can mean that even on a cloudy day, or if there was a volcano that went off, you could still take pictures of things that are happening on the ground. And then light is made up of all different types of colors. And if you look at separating those color bands, you can do some interesting things. So this one is looking at a vegetation index, which kind of looks more at green light, and you can see how healthy certain areas of the ground are. And this can be quite helpful, looking at things like deforestation or helping farmers understand if their crops are healthy. And then there's moisture indexes. So this is another quite interesting thing. So you can look at where there's maybe more moisture on the ground. Is there flooding, or does a farmer, need to put some more water in their field in one area and not so much in another? So satellites can be used for lots of interesting things for the benefits of humans. And there's lots that that doesn't really meet the eye. I think that this is a little bit of an analogy. You've got the kind of three major kind of constituent parts of any kind of rocket launch. You've got your thing that sits at the top, which is the payload. That's the kind of the interesting satellite thing, the thing that everyone talks about. And that's the kind of common misconception. Maybe everyone thinks that the space industry is just full of brainiacs, just full of scientists and engineers. And that's kind of, they are in there, but it's not the whole thing. So when you launch a rocket, you've actually got the rocket, you've got the thing that guides it, you've got the engine. And in the space sector, that's things like people that are kind of guiding where does a business go? Do they want to be developing their business in one section or the other, or a project manager saying we need to kind of focus more in this area or another? So they're not all just these scientists and engineers. And then you've got the ground support. So, we saw in Daisy's images, they've got the satellite dishes, the antennas down in Goonhilly. You've got all the people that are there on the ground control saying, go, go, go. And that's anybody that can kind of be part of any business. And they're really the real heart of any business. So you've got people in sort of finance and legal, any kind of managers, anybody in HR. And so it takes all of these different types of people that make any old business work. And it's the same for any space sector business. And it's the same for launching satellites. So yeah, just don't constrain yourself, I guess, is the main message. Don't just think that the space sector is just about this little blue cone that sits on the top that's filled with the satellite. There's lots and lots and lots of constituent parts. And to show you one final picture, which just shows what the space sector looks like in the UK, there's absolutely loads of it. Each one of these dots in this map represents a UK space sector organisation. You can see, yeah, they're clustered mostly in the south of England, but they're everywhere in England, Northern Ireland, Scotland, and Wales. And you can see as a quick statistic that there's about 800 organisations, and this is not a complete picture. It probably only captures about half. So yeah, you can essentially do anything and work anywhere in the UK in the space sector. So yeah, hope to see you in the space sector one day. Thank you.
Thanks, Eddie. And I think that was a really good thing to say there, is that there's so many routes into the space sector. And it's really having that open mind about the fact that there's so many different people providing various levels of support. Even you said things like project guidance, project management. It's just such an expansive field. So I think that's a really good shout, that there are so many open opportunities for students into the space sector. We've had some really great questions come in already, so please do continue to send those through. And actually, Eddie, one of the questions which I'd like to ask you is about artificial intelligence, actually. And so the question is artificial intelligence already being used in, the space sector, for example, with the work that you might be doing, or is this something that we're only going to really see in the future?
Yeah, so yeah, absolutely is. So there's various types of artificial intelligence. So it could be something like I'm sure that Sarah's going to talk a little bit maybe about it. Is that if you're exploring another planet, these rovers, we can't talk to them that easily. So they will have to kind of see what's in front of them and kind of classify objects and try to make their own paths. And that's one type of artificial intelligence. It may not be this kind of generative AI, which is kind of making pictures and videos and songs out of nothing, or kind of talking to us. But that's one type of AI, and another is kind of machine learning, and that's kind of helping to kind of be part of that, which is helping sort of rovers on planets get around, but also these satellites that are taking images, like that cloudy day image that I showed you. You don't really want to be sending that back down to Earth if you don't have to, because it's almost the waste of the resources that you've got to send a cloudy picture back down to Earth. So lots of people are now interested in being able to have their satellites understand what is a good picture versus bad picture, or good data versus bad data, and then be able to make those decisions on the satellite itself. And there's various other things like that. It's the satellites getting more and more clever to be autonomous and not really need to be having humans in the loop telling it what to do.
I think that was a great segue to introduce Sarah and the amazing work that she's doing. And I'm pretty sure that, I mean, if not, I'm sure AI is going to play quite a bit part in that work that you're doing. So Sarah, I'm going to hand over to you to talk to us about the work that you do.
Share my screen. Hopefully, yeah, it's gonna work. Hold on. Okay. I have to abandon the really nice pictures and videos I have for you today. Doesn't want to let me share. Okay, it's updated now. You should be able to see the images any second. Okay, so hello, my name is Sarah Motagian, and I am a PhD student working on exomers, which I saw a little bit that you have heard a little bit about today from two of my colleagues in the last session. So talk a little bit about my background, what I do now, and kind of technology in general and the future of space exploration. So, like I said, I'm doing a PhD between the Natural History Museum and Imperial College London, and loosely it's based on the search for life on Mars, but more specifically it's looking at the ExoMars mission and some of the instrumentation on board that mission. So when I was at school, my original plan was either to do something in the sciences or something in law, because I love to argue, and I was pretty good at it. So as I went through my kind of high school career, I tried to keep my options relatively open. So I did the sciences, I did social studies, I did art, because I just enjoyed and had an interest in quite a lot of things. But I will say, I think it was kind of a little bit of a foregone conclusion that I'd find my way back to space, because I've always loved space. I've always loved staring at the stars, like sitting out on the roof in the middle of the night just to see what was happening. So a lot of interest, but I think I was kind of destined to kind of fall back towards space. So when I went to university, I decided to do physics with astrophysics, which actually we all did on this panel. And I got to do a lot of really cool projects. I did things with pulsars. On the left, you can see the Crab pulsar, solar flares, which you can see on the right there, which are these huge kind of twisting magnetic events on the sun. And they were amazing and they were interesting, and I got to learn a lot of really cool things, but it didn't feel quite practical enough for me. I wanted to do something a little bit more hands-on, which in hindsight might have meant doing engineering was a better choice. So in my master's year, for my master's project, I decided to take on a kind of conceptual R&D project, so research and development. And I looked at developing a tiny little microscope for doing in vivo, so that means in the body research for things like the oxygen levels in the blood. So I designed an oximetry system, a tiny little insertable microscope to look at the oxygen content in blood. And it was really, really interesting. I didn't have a medical background, but I was looking at it more from the technology side. And I was like, I love this hands-on, I get to change things, I get to design things, iterate through it and try it out and see how it works. So I knew I wanted to do something a little bit more practical than what my kind of original years at university had given me. And I still wanted to be an astronaut. So I thought a good thing to do would be a PhD in space or planetary science. And very luckily, I managed to find a PhD working on a Mars mission, getting some mission experience the year I graduated. So the mission that I work on is called ExoMars. It should be launching in a few years now. And there's a few reasons why this is an exciting mission and some huge kind of technology demonstrations that are going to happen with this mission. We can talk a little bit more about the missions lately and what the kind of technology they brought to the table is. And hopefully this is going to play nicely for you. So the coolest thing about ExoMars is it has this huge 2-meter subsurface drill on the front that you can see there. So this will look the furthest into the subsurface of Mars any mission has ever done. And you'll probably know a little bit about the surface of Mars. It has really high radiation levels. It's pretty inhospitable to life as we know it now. But the idea for this drill is those 2 meters below the subsurface is kind of a little bit of a safe zone. So it's beyond that destructive radiation barrier, you can start taking out samples, delivering it into the inside of the rover where our analytical instruments are, and to look for signs of life. And now to be able to do that, we have to understand where we are on Mars and what's happening. So I work on the contact instruments. So they're roughly at the top of this image, the head of the rover mast. They're all spectral instrumentation. So the stuff that I work on is aiming to figure out where we are on Mars, what we're looking at, and if it's a good place to look for signs of life. So they're all spectral instruments. Just a little moment on what spectra is. The spectra of an object or a material is a measure of how it interacts with light, so how matter interacts with light. and we can kind of think of them as little fingerprints. So each mineral has a very unique response to the electromagnetic spectrum. If we had an object that reflected all of the light that was shone on it, we would get a straight line at 1 reflectance or 100% reflectance, like this pink line. If we had a material that absorbed all of the light incident on it, we'd get the straight line at 0 or 0%. In reality, everything's a little bit more complicated. They have peaks, they have valleys, they have absorption features, which help us figure out what we're looking at on Mars. And if we know what material we're looking at, so the kind of things that Claire does, we can work out how they formed, what conditions had to be present. Was there water? Was it highly saline? So was there too much salt for life to evolve? Were there carbon, hydrogen, nitrogen, oxygen, things like that that help life to evolve the way it did on Earth? So the instruments that I work on, the biggest is PanCam. So the panoramic camera, it's a really cool dual imaging system that helps us do 3D imaging on the surface, as well as multispectral imaging using its filters. So it looks at our scenes through all of these different filters and gets us a little snapshot of different parts of the electromagnetic spectrum, different parts of the spectra. We also have the high resolution camera, which takes really beautiful high resolution images of whatever PanCam is looking at. And then slightly under there that you can't actually see is the ENFIS spectrometer, which again is a spectral instrument, but instead of looking in the visible where our eyes can see, it looks further into the infrared. So lots of really good diagnostic features there that help us understand what we're looking at. Now, just a little section about how we see with a rover. So our eyes work red, green, and blue, but a rover works a little bit differently. So if we think about our eyes being able to see in these 3 colors, what the rover does is it takes a selection of these images across lots of different wavelengths, not just red, green, and blue, and we can put them together into color images. So on the right here, this GIF you can see is the calibration target on the left and all the different filters on the camera system. And what we can do is we can use this data to calibrate our images of Mars. This isn't Mars, this is Spain. This is on a field trial. Sorry. To get a really nice image of the surface that we're looking at. And then we can start doing spectral extractions. We can start doing some of our machine learning and AI techniques to figure out what we're looking at. And specifically, something that I'm interested in is automating the identification of meteorites on the surface of Mars. So they can be responsible for a delivery of carbon, hydrogen, nitrogen, oxygen, amino acids, and synthesizing something called HCN through their descent in the atmosphere. All of these things are really important for the development of life and the sustainment of life. So the idea is if we find locations on Mars that might have samples like this, we might find some evidence of life from the past. So I'll leave it there for getting towards the end of our session. But if you have any questions about exploring Mars, exploring space in general, or technology, I'd love to answer them.
Oh, thanks, Sarah. Actually, there is a question related to Mars that we received, and it's actually it is a really important question, and it ties in quite neatly, I think, to what you're doing in terms of that search for life. And the question is there any ice or water on Mars?
Yes. So there's actually quite a lot. I wish I had a really picture. There's an amazing picture from one of the past rovers where one of the wheels got stuck and it dragged a lot of the regolith away, so that kind of dusty Martian surface. And there's lots of frozen water just a little bit underneath the surface. So Mars is pretty cold. Most of the water is in ice form, not liquid, but there's a fair abundance of water across the surface of Mars, which hopefully, if we end up sending crewed missions, is something we can utilize. So another kind of in situ resource utilization method of making Mars travel a little bit easier.
Oh, brilliant. And I mean, I would love to continue talking about Mars, and it's such an exciting topic, but we have reached the end of the session. But before we end it, I think I'm going to ask a very important question. It's the same question I asked last year to a panel session. I see Eddie might remember this question coming, which I think we will conclude the session with. So the question to the entire panel is, what is your favorite planet in the solar system? So let's begin. Well, let's begin with Sarah. What happens to be your favorite planet in the solar system?
I feel a little bit bad that it's not Mars, but mine is actually Jupiter, for a couple of reasons. It's beautiful. It's really, really cool. It has a giant storm that's bigger than the entire Earth, and I just think that's really amazing. You can see it from the satellite imagery, and it has really cool X-ray aurora around its poles, also really beautiful.
Good job, good job. Jupiter was our guest planet for last year's Mars Week. So let's go over to Daisy. What's your favorite planet in the entire solar system?
My favorite is definitely Venus. I find some of the science that you can do just by looking and observing Venus is fascinating. It's got a really high concentration of carbon dioxide in the atmosphere, so we can use that information to help us study what would happen to the Earth if the concentration of carbon dioxide really increased in our atmosphere. It can tell us a lot about what happens with global warming. So it's like almost an invaluable, it's just there in space. And from that, you can discover things that will happen eventually on Earth. And I think that's amazing.
And finally, Eddie, what's your favorite planet?
Yeah, so if I was constrained to having to pick a planet, I'd probably have to say Earth, just because it's so diverse, so rich in life and interesting things. But I think what I said last year, what I'll probably still just say again and for the rest of my life, is that in the solar system, my favorite thing is no planet, and it's the sun. It's just got so much, it's so many things to learn, so interesting. We don't know the half of it, so the sun is just the most interesting thing in the solar system, in my opinion.
Well, I mean, I said it before. I'm going to say again. Mars. Mars is my favorite planet in the entire solar system, and maybe one day we will be broadcasting Mars Day from Mars. Who knows? I mean, with technology progressing at the rate it is, any students watching today, yep, you might be joining us for Mars Day from Mars within the next couple of years. So that would be amazing. But a big thank you to our brilliant panel for today. And I say we would love to talk about Mars for the entire day and the technology involved, but we have to move on. And I can say that Mars Day does not end here. The next session will be starting very soon, which is about engineering in space. And you don't have to do anything at all. You can just wait on this link and the next session will begin shortly. So from our side, it's a big thank you to all of you for joining us for Mars Day, and to our brilliant panel. Thank you so much for sharing your time with us today.